Okay, good afternoon, guys. My name is Harry Longo, and this is the continuation of sets. We are going to look at the relative complement of a set. In the last lecture, I I I I told you to say I'll be using my own lecture slides because the previous two lectures, I was using someone else's lecture slide, and like I told you, I didn't own the right to share somebody else's content. I don't own the right to share somebody else's content. So I thought of it, and I decided to be making something of my own. Yeah, so um it might not contain a lot, but yeah, I'll perfect it I'll perfect it as time goes on, as time goes by, as we go on. Yeah, and how I'll be answering questions, we'll be learning from there. Okay, so we may begin. So what is a relative complement of a set? So like you've seen here, let X and Y be non-empty sets and U be the universal set. The relative complement, also known as set difference. So when you just see difference, we are talking about subtraction, minus. So when you've been given set X and minus Y, that's an, an set difference or relative complement. Okay, so it's given by X slash Y. Okay, so let me make one correction. It's supposed to be like this slash Y and not the way I've written it. X slash, I mean, X slash Y is wrong. Yeah, okay. So take note of this correction. Okay. Okay, so it's a set of elements which belong to X but are not in set Y. So what do they mean? So if you've been given like set X, okay, set X, then you have something like 1, 2, 3, 4. Okay, then set Y, you have something like 2, 4, 6. If you've been asked to find, maybe they've asked you to find X, God, Y. Okay, X equal to 1, 2, 3, 4. Okay, maybe even 5. Maybe even 5. And then Y, you have 2, 4, 6. Okay, then they ask you to find X slash Y. Then you're going to have something. So when they ask you to find this, it means they're asking you to find the relative complement of X and Y, meaning you have to subtract the elements. Okay, these are the elements in X which are not in Y. So you have to remove all the elements which are in X and also are found in Y. So remove them. So you can see 2, you can also see 2 here, you can see 4 here, you can also see 4 here. So they just want all those elements which are in X but are not found in Y. So we have 1, 3, and 5. I will repeat that. Relative complement of a set. These are the elements which are in set X and not in set Y. So it doesn't mean you have to write all those elements which are remaining. As long as you have removed all those elements which are in set Y, you don't have to include the 6. We are just interested in elements which are found in set X and not in Y. So these are the 3 elements, 1, 3, and 5. Now, what if they ask you to find Y, X, meaning all the elements which are in Y and not in X. So you're going to remove this and this will go, this and this will go, and you will write 6 as the only element. So this is how we find, oh god. Okay, sorry about that. Okay, so that's how we find the relative complement of a set. And then this same relative complement can be represented by either x slash y or x minus y or x like this. So don't be confused. Either of the three, they are talking about the same thing. Okay, so the diagrammatic representation of a relative complement is here. Or let me use the blank space here. Okay, let me use the blank space. All right. Okay, so I left a blank space here for saving. So if we've been given like set x at 1 2 3 4 5 and set y as 2 4 6, so if we were to represent that in a Venn diagram, it would be like, okay, like this. Okay, then we have something like this. Yeah, something like okay, something like this. Okay, so this becomes our y, this one becomes our x. So in set x, okay, so we had 2 and 4 which were common, and then in set x we had 1 3 and 5. Then okay, then in here we had 6. Okay, so this is the diagrammatic representation of what I was talking about in the previous example, the same example but the diagrammatic representation. So if we were to shade like the previous answer we had of x slash y was 1 3 and 5. If your memory serves you well, you'll be able to remember that this is what we found. Now if we are taught to shade, so we'll shade this part. We will shade this part where we have 1 3 and 5. We shade. Okay, we just shade this part. Okay, shade. So I'm going to shade this. Okay, all right. Okay, so this is our shading. So if you look at this, then you notice that this is what we have here. This is what we have here. This is what we have here. If we assume this is our x and this is our y. So that is the relative complement of a set. That is what you know about the relative complement of what? A set. So this is the universal there. Okay. So if there is any question, please feel free to comment in the comment section, to drop a comment in the comment section. If at all you don't understand or you need clarity, you feel like you don't get their contact details, you can get in touch with me and then I'll be able to assist you. Okay, so we talked about the relative complement of a set. Now we are talking about the symmetric difference of a set. Symmetric difference of a set. So the symmetric difference, which is sometimes read as x or plus y, x or plus y. So if you see something like this, they are talking about the symmetric difference. Actually, this is what was supposed to be here. here, yeah, here it's supposed to be this symbol. Okay, so don't forget we are talking about the symmetric difference of a set. So we are saying the symmetric difference of set x and y is denoted by x o plus y, whereas x o plus y is the set of elements which belongs to x or y but not to both x and y. What does this mean? Elements which belongs to x or y but do not belong to both x and y. So I'll give an example. Okay, so let me give an example of what I'm talking about. You might have set x as a, b, c, d, e. Get ka? Then y, r, a, e, o, r. So then they ask you to say find the symmetric difference. So we are saying symmetric difference are those elements which are found in both x and y. I mean x or y, but do not belong. They are found either they belong to x or y, but do not belong to both x and y. So what they don't belong to both x and y. So remove these which belong to both x and y. This, and then write what is remaining. It's a bit similar to what we were doing previously, the relative complement. But the difference is that in relative complement, we do not write all the all the all the elements, which we only write the elements of the specified set. In this case, we are going to write O. So xo plus y will be equal to everything now. B, I, O, U, C, and D. Okay, so B, I, O, U, C, and D is the answer. E is the answer. So let me show you the diagrammatic representation of what we are talking about. Okay, so let me illustrate what I was talking about in in that example. So now here I'm using a diagram. So we said x at a b c d e, x at a b c d e, and then y at r a e or r. So if we look at set x and set b, if we remove those elements which are both in set a and set b, so we in x we had something like we had something like x, we had something like we had a, b, c, d, e, and then with y we had something like r, a, e, o, o. So if we look at a, we are going to cancel it. If we look at e, we are going to cancel it. Okay. So the elements which are found in both a and e, I mean both x and y, are a and e, and then we write the rest. We write the rest. This is I O U, I O U, and then here we're going to write. Oh my God, I'm making a mistake. I made a mistake. Okay. So we are going to write B C D, B C D. Then here we are going to write I or U. Now we are saying symmetric difference is the set of elements which are found in X or Y, but not in both X and Y. Not in both X and Y. And the elements which are found in both X and Y are A and E. So we don't want them. Therefore, we are going to shade these the ones we want. The ones we want. Okay, so we are interested in only those elements which are not found in both X and Y, but yeah, in both X and Y. No wonder we have shaded at the outside and we have not shaded the intersection. So this is about symmetric difference. You have to be careful with the relative complement because they are a bit similar, but the difference is the one I explained earlier on. Okay, so this is how we shade, like the diagrammatic representation. Okay, so we go to an example here. We have an example. So they're saying given the sets P 2468, then Q 1 2 3 4, then R we have 3579. Find P slash Q. P okay P slash Q. So P slash Q are all the elements in P which are not found in Q. So if we look at the elements in P which are not found in Q, so we will see that 2 is found in both, 4 is found in both, 6 is not found in Q. Remember, P slash Q, elements in P which are not found in Q. So here the answer is 6, comma 8, because they are saying P slash Q, which means the elements which are in P which are not found in Q. Okay, so we are still talking about relative complement here. Okay, so we have answered the first question. Let's answer the second question. We have Q slash R. Q slash R. So Q slash R, the elements which are found in R, the elements in R which are not found in, the elements in Q which are not found in R. So which are those? So 1, okay. Okay, so the elements in Q which are not found in R. So 1, 2, and 4. So 1 and 2, 1, 2, and 4 are not found in R. So it's 1, 2, 4. That's the answer. Because 3 is also found in R, but you are not interested in what is found in both, but what is in Q and not in R. That's what you're interested in. So that's the answer. Okay. So let's find Q. Okay, let's find Q slash P. So Q slash P, elements in Q which are not found in P. Elements in Q which are not found in P. So elements in Q which are not found in P, what are those? Elements in Q which are not found in P. So we have 1 is not found in P, but it's in Q. We have 3, which is not found in P, but it's in Q. So this is the answer. Okay. Okay, so let's answer the last one, which is R slash, okay, slash Q. Okay. So I'm slow. I want everyone to understand. Okay. So R slash Q meaning elements in R which are not found in Q. Elements in R which are not found in Q. So elements in R which are not found in Q is the entire set R, which is 3, 5, 7, and 9. Okay, so this is the answer. And the last question is find okay, sorry, this was an error. It was supposed to be P, it was supposed to be P O plus Q, meaning elements which are not found in both Q and P. Elements which are not found in both Q and P. What are those elements? So note the difference between P slash Q, P slash Q, and PO plus Q. In P slash Q, we were interested in elements which are found in P but not in Q. And our answer was 1. Elements which are found in P and not in Q. And our answer was 6, 8. Now, note the difference with P, P slash PO plus Q. So I want you to note the difference. This is where symmetric difference and relative complement differ. So for PO plus Q, we want elements which are not found in both P and Q. So which are those? We have 2 and 2, no. 4 and 4, no. So you are going to write 6, 8, 3, 1. The order doesn't matter. So this is the difference between relative complement and symmetric difference. You've seen in relative complement we were only interested in those elements which are found in P and not in Q, but in symmetric difference, in symmetric difference, we are interested in all the elements which are neither found or which are not found in both P and Q. Okay, so that's it. We come to the laws of sets of algebra. Laws of sets of algebra. Okay, laws of sets of algebra. We have 7 laws of sets of algebra. So X union X, we start with the idempotent law. Idempotent law states that if you unionize a set with itself, it will give you that set because we don't repeat elements twice. Okay, so let me illustrate what they are. All right, sorry. Okay, let me illustrate what is being talked about here. Idempotent law is saying if we unionize a set with its set, we are going to get that same set. So for example, if we have X, this is equal to 1, 2, 3, 4, 5. And then we say X union X, meaning we unionize X with itself. Since we don't repeat the same elements in sets, we don't repeat the same elements. Just because we are unionizing X and Z, we don't need to write 1, 1, 2, 2, 3, 3. No, this is wrong. This is wrong. So we just write once. So 1, 2, 3, 4, 5, which is equal to set X itself. So no wonder idempotent law is saying X union X is equal to X. Okay. So here. So it's the same if you intersect. It's the same if you intersect. Previously we had okay, we had something like all right, okay. We had something like x intersection x intersection x, meaning we had maybe x is equal to 1, 2, 3, 4, 5. You get? So if you say intersect x intersection x, meaning what is common between x and x? What is common between x and x is the entire set again. So no wonder it's saying x intersection x is still x. So that's all about the idempotent law. Okay, so that's all about the idempotent law. Okay, so let's go back to the commutative law. So commutativity is all about what you start with. It's not a respecter of what to start with. That's all I can say. So let me give you an example which is outside um, um, what you're talking about. For example, if they say, okay, addition and multiplication are commutative, what do they mean? So if you say 1 plus 2, it's the same as saying 2 plus 1. Both answers, both cases will give you answer 3. 1 times, okay, 2 times 3 and is equal to 3 times 2. Both cases will give you answer what? 6. That's all about commutativity. So when we say multiplication and addition are commutative, we mean they are not respecters of what to start with. Yeah, unlike subtraction and division. So if you say 1 minus 2, it's not the same as 2 minus 1. It's not the same. They are not equal. If you say 1 divided by 2, it's not the same as 2 divided by 1. So it's the same even here. It's the same even here about the commutativity of sets. So sets are commutative. If we say um, X union Y, it's the same as Y union X. It doesn't matter. The order doesn't matter. So in this case, commutativity has to do with the order. It's not a respecter of what you start with. Whether you've been given like to say X is equal to 1, 2, 3 and Y is equal to A, B, C. And then if they say X union Y, obviously you will start with 1, 2, 3, A, B, C. It's the same. It's the same thing even if they ask you to say Y union X. You start with A, B, C, 1, 2, 3. If you want, you can jumble them. So that's all about commutativity. And it's the same even if it's the same even when you say X intersection Y, it's the same as Y intersection X. It's the same. So these are the laws you need to. Okay, associative laws. Associative laws also states that if you start the brackets, if you start with uh, uh, X intersection Y in the brackets intersection Z, it's the same as if you get this bracket here, you bring it here, and then you get this one, you take it here, you have something like X intersection open bracket Y intersection Z. These two are the same, they are equal. That's what associativity is all about. So it doesn't matter whether you use which bracket or you start with which, it's okay. Yeah, so it's the same as union. You can start with X union Y open bracket union Z. Union Z, it's the same when you start with uh, uh, X union Y union Z. So that's about associativity. Okay, okay. Let's come to distributive laws. Distributive laws are similar to associativity. The only difference is that in distributive laws we have two operations. We have intersection and union. So if you say, so I want you to pay attention on this now. So if you say X intersection Y union Z, get these two, put them in one bracket, and use this symbol, put this symbol in between, and get this again, this together with this. So what I'm trying to say is, when you want to distribute this, write x intersection y close union x intersection z. It's more like this x outside is multiplying what is in the bracket. The same way we do when you have a scalar. When you have a scalar, for example, let's say uh, 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 a 2 open bracket 3 plus 4. What you do is you write 6 plus what? 8. 6 plus 8, which is equal to 14. It's the same thing if you add these guys, you have 7. 2 times 7 is 14. So it's the same thing which is being done here. X intersection y union z is, get this, x intersection y close union x intersection z. This is being found in both. So if you want to reverse this, just factorize. So just factor out this x intersection y and write what remains. This, and this, y union z. Simple. Okay, so it's the same thing if you have x union y intersection z. Okay, so you say x union y close intersection x union z. If you want to come back to this, just factorize x union, okay, y, write what remains, this, and this, y intersection z. Okay, so that's it. That's all about distributive laws. So we come to identity laws. Identity laws, say for identity laws, you have x intersection empty set is equal to empty set. Why? Because there is nothing common between set x and the empty set. For example, if you have x as let's say x, okay, x as 1 2 3, and then you have an empty set here which has nothing in, and then they ask you to say x intersection empty set, meaning they're asking you to find what is common between x and empty set. Nothing. There is nothing common, hence empty set. That's the answer. What about then they ask you to say find x union empty set, x union x union empty set. Okay, they wanted to unionize x and empty set, so the answer is x itself, meaning put together x and nothing, you still have x. So that's all about the identity laws. Okay, so let's talk of the complement laws. Okay, so we have x union x complement is equal to a is equal to universal. Okay, so let's say we have the universal set. You have the universal which is u is equal to numbers 1 to 10. Then you have x which is equal to prime okay, let me just say odd even numbers between 1 to 10, which is 2 4 6 8. And then they ask you to say find x complement. X complement are those numbers which are not, or those elements which are in the universal which are not in those numbers which are in x. Or x complement, I can say those elements which are in x or those elements which remains in the universal after removing those elements which are in X. So we are going to remain with 1, 3, 5, 7, 9. Okay, so here I left one even number, which is 10 itself. So 1, 3, 5, 7, and 9. So this is X complement, this is X. So if they say X union X complement, we'll mix all these, which is 1, 2, 3, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, which gives us what? The universal set. Which gives us the universal set. Hence, X union X complement is equal to universal. But if at all we say X intersection X complement is equal to empty set. Why? Because there is nothing common between what is in X and what is not in X. There is nothing in common. Okay. So that's it. And then if we have a complement of a set and a complement outside, complement of a set, these two guys will cancel and will come up with X just. Okay. So that's it. And then we have De Morgan's law. Let's come to De Morgan's law. If you have A intersection B close bracket complement, or some people will use a C. So when distributing this, make sure you change the sign here. This sign changes to what? Union. So you have A complement union B complement. If you had union, if you had intersection in here like this, when distributing you say A complement union B complement. Okay. If you had union inside A union B complement, you say A complement intersection B complement. So that's all about De Morgan's law, and this marks the end of this lecture 1 about sets. Okay, thank you very much, guys. Yeah, so if you want to get in touch with me, you can WhatsApp me. I'll leave my line in the description, and yeah, you can email me and my email will be there, or you can inbox me on Facebook. My username is Harry Lungu. Thank you very much. God bless you.